Hi, in the previous video we talked about big O notation. Let us now talk about omega notation or big omega notation. Omega notation is opposite of big O notation. Big O notation is used to provide an upper bound. Omega notation is used to provide a lower bound. Let us take a look at the mathematical definition of omega notation. The definition says that Fn is equal to omega of Gn or big omega of Gn if and only if there exist positive constants C and N naught such that C of Gn is smaller than or equal to Fn for all n greater than or equal to n naught. Like big O notation, here also we talk about large values of n, right? N tends to infinity. And this condition is just opposite. In big O notation, we were saying Fn is smaller than or equal to Cgn. Here we are saying Cgn is smaller than or equal to Fn. Let's take a look at this example. We are given Fn equal to 2n plus 3. We can always take the highest growing term and write it as big omega notation, like big O notation. Please note that both big O and big omega, they cover equal to as well. So you can put same order of growth in big omega notation. If I ignore the lower order terms, I can ignore the 3, I can ignore the 2, and I find the order of growth as n. So I can put that in omega. Right? That's a shortcut to find the order of growth, and exact order of growth can be put in omega notation. Let's see another example. Say I have 2n square plus 3n plus 6. What do? We ignore the lower order terms, ignore the leading constant, we get n square, and we can write it as omega n square. Right? That's one way. Now how do I prove it? How do I use this mathematical definition to show that this is 2n plus 3? We need to find C and N naught such that C of Gn is always smaller than Fn. In big O notation, we were taking the constant of leading term and we were incrementing it by 1 and we were using that as C. In big omega notation, we are going to do opposite. We are going to take the value which is just smaller than this 2. Right? So 1 is something that we'll take. So I'll take 1 here. Right? And I'll say C is 1. And since this was n plus 3, then I could have taken C as 0.5, right? Smaller than whatever is there in the constant of leading term. So I've taken 1, so my Cgn is n, right? And we want to show that this is smaller than equal to Fn for all values of n greater than equal to n naught. Let's try to find out n naught. So what do we want to show? We want to show that n is smaller than equal to Fn, which is 2n plus 3, right? So for what values of n, it will be smaller than this? For all values which are greater than equal to 0, right? So you can choose n naught as 0, right? You can in fact choose it as 1, 2, 3 or any positive value, but you have an n naught after which this value is always going to be greater than or equal to this value. So if we put n naught equal to 3, we have now two constants, the required constants, and we have this condition followed that this is smaller than equal to 2n plus 3. So we can clearly say that this is equal to omega of n. In this graph, the same thing is shown pictorially. We have Gn here and we have Fn here. And we can see that for all values of n greater than equal to 0, we have Gn is smaller than Fn. For n equal to 0, it's 3. And this is 0, right? So this is always greater than equal to, its order of growth is also higher. You can see it's going to be like this and this is going to be like this. So it's always going to be smaller than this value. So this is pictorial representation. What was happening in big O notation? We were having a line which was going at a higher growth like this. So your big O of function, it bounds from the upper side omega function bound from the lower side. Let us now talk about some important things about omega notation. One thing is, when you say a function is omega n, it covers all order of growth or all functions which have order of growth as linear or greater than linear. So omega n covers functions like n by 4, n by 100, n by 200. So all these functions have linear order of growth, right? All these functions have linear order of growth. This is linear, this is linear, this is linear, this is linear. Please remember the rule. You can ignore the lower order terms, you can ignore the constants of higher order terms. So it's n, it's n, it's n, it's n, it's n, all these linear. Any order of growth which is greater than linear, that is also covered by omega n, because it bounds from the lower side, right? You can always find a c and n naught such that c of gn is smaller than f of n when f of n is any of these forms for all n greater than n naught, right? C will simply be 1, and you can clearly find n naught, right? So all such functions, anything which is having order of growth higher than n is covered in omega of n. But in general, it's a good idea to use the tight bounds, right? Use omega n only for functions of this form and use omega n square for functions of this form, right? In general, we should be using tight bounds, whether we are using big O or big omega. Now, one more interesting fact, if Fn is equal to omega of Gn, then we can say Gn is equal to big O of Fn. We just saw the mathematical definition of omega, and we saw previous video that mathematical definition of big O, and they are just opposite of each other, right? So what it means, Gn is having lower or equal to order of growth than Fn when you say Fn is equal to omega of Gn, and here what it means, Gn is having lower or equal to order of growth than Fn when you say Gn equal to big O of Fn. They both are the same things, right? Now third thing, omega notation is useful when we have lower bound on order of growth. In algorithms, sometimes what happens is you have lower bound on time taken by the algorithm. For example, consider an n-player game which keeps on running in an infinite loop while players are playing the game. However, this game's code, it runs a loop for n players, initialize their scores as 0, right? Ask them for the next move, and when any of these players it quits, the game is over. Now, what is the time complexity of this program? There is no upper bound, it keeps on running as long as the players are playing. But there is a lower bound that this program takes omega of n time, because there are n players playing, it has to initialize their scores. Now it's up to the players how long they want to play. So when you have a lower bound, when you can represent a program by using its lower bound, you use omega notation, right? The n player game, its time complexity can be said as omega of n. We are saying that it will take at least linear time, it will grow at least linear in terms of input size. If there are more players, it will be more linearly, but we do not know anything about the upper bound or the exact time, but we know about the lower bound.